Perfect. Good morning. Got just a few more people coming in. Okay, perfect. Let's see. Welcome, everyone. Welcome to day 3 of the 2022 Open Data Workshop. Let's see. Some trouble with the video. Okay. Open Data Workshop. Okay, great. Welcome to day 3 of the Gravitational Wave Open Data Workshop 2022. We are so happy that you are here today. Thank you for joining us. Our first talk today is going to be by Aditya Vijaykumar. Aditya is a research scholar at the International Center for Theoretical Sciences. And today he is going to tell us about parameter estimation. Good morning, Aditya.
Good morning, and thanks, Jonah, for that introduction. And thank you to everybody for joining. Jonah, I think I need permission to share my screen.
You're right.
Okay, I got it now.
Yeah, sorry for that.
Right, so thanks everybody for joining. My name is Aditya, as Jonah just mentioned, and I come from this, I come from this institute called International Center for Theoretical Sciences in India. I'm also a part of the LIGO-Virgo-Kagra collaboration and also the LIGO-India scientific collaboration. And today I'm going to be telling you about how we estimate source parameters from gravitational wave signals. Okay, so what is indeed the problem of source parameter estimation? The problem is to go from these wiggles in our detector that we see, and you've probably heard about this quite some bit in the last 2 days. How do we go from these wiggles that we see in our detector to the measurement of parameters of the signal, say the mass of the black holes in a binary black hole signal? Right? But you would ask, why do we care about estimating parameters? I think most of the answers were given by Maya's talk yesterday. But one of the things is that it's not just enough to detect gravitational wave signals. We want to understand the physics and astrophysics behind these signals. For instance, we want to understand, say, what's the equation of state of neutron stars that yesterday was mentioned as well. We want to, say, perform tests of general relativity. We want to see how well these signals agree with predictions from Einstein's theory of general relativity, and for much more interesting and impactful science. All these problems actually involve parameter estimation in a very, very fundamental way. Okay, so just to give you an overview of what's to come in the slides, what are the tools that we use to actually estimate parameters from the data? So the first thing that we need is models for both the signal and the noise, and we'll talk about that a bit in the next few slides. We need this really, this theorem that maybe most of you had studied in your high school. For instance, it is called the Bayes theorem, and this deals with conditional probabilities. Specifically, it says that the probability of event A happening conditioned on event B is equal to the probability of event B happening conditioned on event A multiplied by P of A happening divided by P of B. I hope everybody's familiar with this, but we will talk about this a bit more in our future slides. We need these things called stochastic samplers. Stochastic samplers are basically the tools that we use to efficiently find the probability distributions that we actually want to measure. And combining all these things, we need some nice code. And this is where the parameter estimation package called Bilby comes in. And I'll talk about Bilby a bit at the end of my talk. And you can also, the day 3 tutorials also have Bilby in them, and you can basically play around with the various functionalities Bilby in there. Okay, so let's just understand the signal and the noise first. So the data that we observe in our detectors, D of t, has a lot of noise, and there's some signal embedded in that data. And I can write the D of t, let's say my data in the time domain, I can write it as a sum of a signal, which is also in the time domain, expressed in the time domain. This signal is contingent on a set of parameters theta. Now, this set of parameters theta could include the masses, the spins, the distance, the sky location, so on and so forth, and the noise. And when I add the signal and the noise together, that's when I get data. I could equivalently also take Fourier transforms of these time domain objects and get and express these quantities in the frequency domain or the Fourier domain. Okay, so let's just talk about the signal for a few moments. This gravitational wave signal has 2 polarization, exactly like light. And these 2 polarization are the so-called plus polarization of the gravitational wave and the cross polarization of the gravitational wave. And both these polarizations are described by 15 parameters in case of a binary black hole. These include intrinsic parameters, that is the masses and the spins. So the mass of the 2 black holes involved in the merger, the 3-dimensional spin vectors or the angular momentum vectors of the black holes each, and also extrinsic parameters such as the distance, the sky location, and something called the polarization angle, etc. And given these 2 polarizations of my gravitational wave, I can write the total signal h of t given theta. Sorry, I just changed the notation slightly a bit here. I can write that as something that depends on the polarizations, which is again a function of the parameters themselves, and a factor which depends on the sky location and the polarization angle of the binary with respect to us. So, these factors are called the antenna pattern functions. Okay, so just let's discuss about how the signal really looks and what the effect of varying the parameters on the signal is. For instance, if you have a higher mass signal, if you take, let's say, a signal with mass 1010, and then you compare it with a signal of mass, let's say 2020 for the 2 black holes involved, a higher mass will always give a shorter signal, but it will give more amplitude at the same distance. For instance, you can see it here. When I increase the mass, when I go from low mass to high mass, the signal itself becomes shorter, but the amplitude of the signal, the strength of the signal actually increases. Okay, so this is the effect of varying mass on the morphology of the signal. We could also imagine, changing the spins. So I'll just pause the video for a second and talk about what is being done in this video. This vector is perpendicular to the plane of the rotation of the binary. And it is also the direction of the orbital angular momentum of the binary. And if the individual angular momentums of these black holes, we call them spins, if those spin vectors are actually aligned to the angular momentum, and in the positive sense, so they are aligned to the angular momentum or parallel to the angular momentum, that essentially increases the length of a waveform. If there's 0, so compared to the case when there is no spin at all. And if these 2 spin vectors are anti-aligned with the orbital angular momentum, that decreases the length of the waveform, as is shown here. The binary with the spins anti-aligned merge first, followed by the one with 0 spins, and finally the one which has spins aligned to the orbital angular momentum merges the last. One very interesting thing that happens in binaries where the spin vector is no longer aligned with the orbital angular momentum is that the orbit starts precessing. And when that happens, there are these discernible amplitude variations that you can see in the waveform. And that's a very interesting feature of precessing systems. Both these visualizations were actually taken from this nice package called the Binary Black Hole Explorer. I would encourage you to download that and probably play around with that as well. Okay, let me Go forward. Okay, so that's it for the signal. And we talk a bit about the noise now. Some of this has already been covered in Pekka's lectures yesterday. But just to repeat, the noise property is generally unknown and need to be calculated from the data. And given a data stretch, we have to calculate the noise properties. And contingent on the following assumptions, the assumption that the noise is stationary, that is, the noise properties do not really change with time, and the assumption that the noise is a colored Gaussian, which means that the noise properties are different at each frequency, but described by a Gaussian process at each frequency. We can describe the noise properties by the power spectral density, which is denoted by S subscript N of F in the frequency domain. So we can describe the properties of a noise by a power spectral density, which roughly looks like this. So this is data from around the event GW15 and 14, and this is what the power spectral density for that event, for the data around that event really looks like. Okay, so you can think of the PSD as being proportional to the variance of the noise at each frequency. When I say variance, I mean it in the sense of the Gaussian distribution. So there's a mean of the noise which is taken to be 0, and the variance of the noise is basically given by being proportional to the power spectral density. And what I can say is that the probability of getting a noise sample Ni at any frequency Fi is proportional to a Gaussian. This is something that looks like a Gaussian at least. So you have some Ni square in the numerator, and you have the Sn of Fi in the denominator, which essentially also sort of tells you that the power spectral density is also looks like the variance of the noise. Okay, how do we estimate the PSD from data? One of the more famous methods is to use the Welch method. What this involves is dividing the time series data into small segments. They could be overlapping segments as well, and taking the Fourier transform of each segment. Calculating the Fourier transform of each segment and calculating the mod square of that quantity and averaging it over all segments. So naturally, if we have more data to average over, we'll have a more accurate estimation of our PSD, which is shown in the plot on the right. So if you just take a 64-second data and do the PSD, you'll get some noisy kind of curve. But if you take, let's say, 1,024-second data and do the PSD of that data, you'll get a more accurate estimate of your PSD. Okay. Right, so once we've learned about the signal and the noise, we jump on to talk about the Bayes theorem, which I briefly also mentioned in one of my earlier slides. So what I'm going to do is I'm going to take the Bayes theorem, which I have already mentioned, and change A to theta, send A to theta, and send B to D, which stands for data. Just by changing the notation, what I get is P of theta given D equal to P of D given theta multiplied by P of theta divided by P of D. Now notice that I will promote all of these to also a probability distribution. Here we were talking about individual probabilities, but now we will think of these P's as probability distributions, and we'll also give these probability distributions their own separate symbol. So we'll call the left-hand side the P of theta given D by the small p. This is called the posterior distribution of parameters. So, and we'll call this P of D given theta by the curly, the curly L, and this is L of D given theta. This P of theta goes to pi of theta, and we'll call the thing in the denominator by just the ZS, which is called the evidence. The pi of theta is called the prior, and the curly L is called the likelihood. We will talk about each of these in some detail in the next few slides, but understand that we want the problem of parameter estimation is to actually estimate the left-hand side of this equation. It's called the posterior distribution, the probability that a set of parameters theta describes the signal. Right. Okay, so let's go on and understand terms in this equation. The first thing is the likelihood. So we know that, likelihood is basically the probability of D given theta. We know from the noise properties discussion that we just had earlier, that at each frequency, the residual after subtracting the best fit signal from the data should look like noise. And hence, it should follow a Gaussian distribution, right? Because the noise follows a Gaussian distribution at every frequency. Hence, the likelihood function distribution can be written as a Gaussian distribution in the residuals. That is, for each frequency, we can write the probability of getting di given theta as proportional to some exponential of d minus h squared. So what I essentially mean is, if I take the data and subtract my signal from it, I should get noise. So this is basically just noise. And I square it and divide it by the past spectral density. This is just, I mean, in some sense, I've just sent ni to di minus h. But this allows us to formulate a likelihood function which will turn out to be extremely powerful, as we'll see in the next few slides. The total likelihood for across the frequencies, because our signals are generally broadband signals and do not really reside at just one frequency, the total likelihood can be written as just the product of likelihoods for all the frequencies. Okay, fine. Let's go to the prior. Now, the prior distribution encodes the prior knowledge or belief, our prior knowledge or belief in what the parameters of the system ought to be. So this is really a distribution that the analyzer, the data analyzer, will set based on their prior knowledge or belief of the system. But there are some examples that might aid you in setting the prior distribution. So for instance, we do not expect that any of the directions in the sky are more probable to produce gravitational wave events. So what the prior on the let's say the sky location will be uniform in the sky area. We also, let's say, do not a priori assume that we have a lot of information about the mass distribution of, let's say, binary black holes. We'll put the prior on the masses of the binary black holes to be uniform. There are other priors that come just because there's a physical limit on something. For instance, there's a physical limit, or at least thought to be a physical limit on the maximum spin of neutron stars. And that means that we should restrict our prior on the magnitude of the spin to be less than, say, 0.89, and so on. As I mentioned, and I reiterate, this is a choice that we make when we're doing an analysis, and of course we need to justify that choice, but it is choice that we can make while doing the analysis. Okay, so there was something in the denominator which I forgot to say, but was an overall sort of normalization constant of the right-hand side. And this number, Z, was called the evidence. The evidence is actually used to compare different hypotheses for the data, say different signal models and so on. One very simple example of where the evidence is used is in comparing signal and noise. So say we want to find out how significant is the fact that we have detected the signal. Oh, that's not detected. Let's say how significant is the fact that the data contains a signal as compared to the hypothesis that the data contains no signal and just contains noise. We calculate the evidence, formulate the evidence for the noise at just Zn with just saying that we just write it as the likelihood without the h on the inside the exponential. So it's just the mod d of fi squared divided by Sn of fi. And this is the so-called noise evidence. And the base factor of signal versus noise is just the ratio of evidences. So the base factor is just Zs, which I defined in the earlier slide, divided by Zn. Now, if the base factor is, say, above a certain cutoff, say 3000, we say that there is evidence for the signal being present in the data. Okay, so I hope that's clear. So we now have all the cool tools to calculate the left-hand side. We discussed about the likelihood, we discussed about the prior, we discussed about the evidence. So we now have all tools to calculate the posterior. But then we run into a problem. As I said, theta is basically a set of 15 parameters. 15 parameters is a very high dimensional space. And if you wanted to calculate, let's say, the right-hand side over let's say a grid of parameters in theta, gridding the space would be extremely inefficient. This is because, as you can imagine, the cost of gridding each dimension and scales exponentially with the number of dimensions. For instance, if you want to use 10 grid points per dimension, but by dimension here I mean parameter. If you want to use 10 grid points per dimension and you have 15 dimensions, the total number of likelihood calculations, or let's say the right-hand side, needs to be evaluated for 10 raised to 15 points. And that is an extremely time-taking process. And that's extremely inefficient, and we cannot, it's not a practical problem at all for our purposes. So the solution is to use stochastic samplers. I had mentioned briefly about stochastic samplers earlier, and I'll give you a demo on the next slide. So the idea of stochastic samplers, I've taken an example of so-called Markov chain Monte Carlo samplers. The idea of this is to populate the prior space with a lot of random numbers in the start. So that is the initial condition, so to say. And for each random number so populated, we take steps towards the direction that will increase probability. And we do that in a random way with the probability that the step is accepted depending on what the change in the probability will be. And what essentially will happen after that is that when we, so the thing, extremely sorry for this. So we start off with numbers populated all throughout the prior space. And as we go ahead, what we see is that all these points that were initially in the prior space converge to, let's say, one point, which was, say, the parameters that we actually put into the data. There exist other sampling methods too, for instance, as nested sampling, which is used very, very frequently in LVK data analysis as well. And there are a host of other sampling techniques. Okay, so, I mean, dealing with the data, calculating the waveforms, calculating the likelihood, sampling on it, and so on, might sound like a lot of work. And that's why we have an open source package called Bilby, which comes to the rescue. So a few words about Bilby. Bilby is a very user-friendly open source parameter estimation library. It can work with existing LVK data, but you can also simulate data. You can take fake noise and inject a fake signal and test your data analysis pipelines on that signal as well. It supports native, by native I mean samplers which are inbuilt within Bilby, for instance, Bilby MCMC, and open source samplers like MC, Dynasty, Multiness, etc. These are just names of Python packages which actually implement these sampling algorithms. And the best part is that you can also use Bilby to do parameter estimation problems in data which is not GW data as well. So for introduction to Bilby, using both real and simulated data, please do check out the day 3 tutorials. Okay, so I'll spend my last few slides on understanding what the output from a parameter estimation run is. So basically, the output from a parameter estimation run is draws or samples from the posterior distribution of parameters. This can be thought of as, say, a spreadsheet. So basically, you have all your parameters. Say, I've just shown 5 parameters here. So for each of those parameters, you have n number of posterior samples, and you can read or process these files with any standard tools. There's typically released H5 files, so you can use HDF, H5py, or NumPy, Pandas, all these standard Python packages. And histograms from these samples will give you the measurement of the parameters corresponding. So histograms from samples of each parameter will give you the measurement of the parameters. So for instance, let's say I take mass1 and mass2, I add them together, I add the 2 values together and draw a histogram of the masses. What I'll end up getting is this. I've taken this from the GW 150914 event and the Bilby samples for the 150914 event. For instance, and this is to illustrate what this looks what the measurement of parameters actually looks like. So this is your posterior distribution, marginalized over all the other parameters, but only for this total mass parameter, which is just m1 plus m2. So what you can essentially do is you can find a region in this posterior distribution whose area is 90% of the total area let's say, 90% of the total area in this distribution. And you can call that 90% credible interval. And that then translates to the measurement of your parameters. So you can quote numbers like, say, 71, with 71 plus 0.53, which is, say, the median value of this distribution, plus 3.32 minus 3.26. And this plus 3.32 and minus 3.26 actually correspond to this and this line or in this distribution. So, so this is for one-dimensional distributions, but generically our output is not a one-dimensional distribution. It is a highly correlated distribution. So one could also try to look at 2D histograms and draw a collection of 2D histograms. By 2D histograms, I mean plots like this. And these are in popular parlance called corner plots. And these are very useful to look at correlations between parameters. For instance, I can point you to the correlation plane of M1 and M2, as you can see here. And you can see that there's a negative correlation between M1, the measurement of M1 and M2. There's also another very nice package which is used by the LIGO-WIGO collaboration called PE summary. And this is a Python package for reading in data and producing and also processing the data. By data here, I mean the posterior samples, processing them and also producing some really, really nice plots like this one. Okay, so that's it from my side for today. I'll leave you with some Bilby, the links to the Bilby and PE summary documentations. And this first paper is the methods paper for Bilby. And this Thrain and Talbot 2019 is a really nice review on whatever I spoke about. So feel free to get in touch with me. This is my email ID. And of course, you can also post your questions on ask.equipment.org. Thank you.
Okay, perfect. Thank you so much. That was a great talk, and we're really grateful for you presenting it with us today. Okay, we'll take a few minutes and see if there are questions. We can use the hand up feature in Zoom. Looks like our first question is from Sadek.
Peter.
Hello, was somebody speaking? I couldn't hear.
Can you hear me, sir?
Yes.
Can you hear me, sir?
Yes.
Thank you very much, Dr. Vijaykumar, for your interesting presentation. I have two questions, and I appreciate if I say wrong, please correct me. My first question is how much accuracy we need in sigma, I mean a standard deviation in a Gaussian distribution to say we have a good data. And my second question is, can we say the noise will raise exponentially during the time and effect on our data, our receiving data? Thank you very much.
Okay, so I hope I got the questions right. So I think the first question was, what is the sigma that we need to say that we have a good estimation of parameters? And the answer to that is that it really depends on the physical problem that you're trying to pose. So for instance, if you say want to if your physical problem demands a really accurate estimation of, say, the sky position, and then you need to have, let's say, sub-degree precision on the sky localization. But there might be some problems which might not need that good an accuracy on the sky position. So you can sort of do away with other values of the sigma, as you mentioned. So the answer is that it basically depends on the physical problem that you're trying to solve. I actually did not get your second question very well. So can you please repeat that?
Yes. My second question is, can we say the noise will raise exponentially during the time and affect on our received data?
Are you saying that?
My question is true or not?
Are you saying that the noise level itself, so are you saying that the PSD itself will change so much that it will corrupt the whole thing? Are you trying to say that, like, let's say the noise properties, the noise level actually goes from something like 10 to, let's say, 10 raised to 4 or something like that? Is that what you're trying to ask?
The noise not going in perturbation methods is not following the methods of the perturbation theory or not. The noise is constant and never rise. And this is my I confused when I understanding the noise in our data, and that noise will raise or no, it's constant.
Mm-hmm. Yeah, so the noise will, I mean, the noise levels can change depending on, I mean, a lot of factors actually. I think you heard a bit about this in yesterday's talk, where the noise level could change even due to, let's say, environmental effects. It could change due to other parameters, say, other things that are happening around the detectors. So yes, the noise, I mean, yes, we made an assumption that the noise properties do not change with time. But of course, a big caveat to that assumption is that we'll only work with data stretches where the noise properties do not change with time a lot. So yes, the answer to your question is that there are stretches of time where the noise properties just change a lot. Yeah, there are times like that.
Thank you very much.
Okay, perfect. And then I did see a raised hand from Luis. Luis, do you want to ask your question? Okay, we'll come back to him. Let's see, next up is...
Okay, here I am.
Okay,
I am ready. Okay, my question is the following. In the physical review letter 128, published 12 May, Vijay Varma and our beloved Professor Silvia Viscovinu said that the event GW 200121 has a great mass gap and a great preceding in the line of sight, and the black hole after the merge was kicked with a great speed, 1,005 kilometers. This question is very important for my personal research. This case would be possible with a mass radio of the initial black holes as large as 6.
Sorry, what was the question? What was the last thing that you mentioned? I didn't quite get that.
It is possible?
Possible for what?
To take to was kicked.
Yeah, so I mean, I think that analysis, I mean, I'm not, of course, one of the authors of the analysis, but I'm aware of it. And I think what they've shown is that the black hole, based on some choices that they make, is kicked, and it seems to be consistent with a kicked black hole. And this happens because there is precession in the actual binary system. And what happens when there is precession in the initial binary system is that after merging, there could be some angular momentum, some linear momentum that the final object has, and then hence it can be kicked out of galaxy. So yes, that is completely possible. Yes.
Okay, thank you very much.
okay, perfect. Our next question is from Divyansh.
Okay, so am I audible?
Yes.
Okay, so my question was regarding that stochastic process that you discussed, Aditya.
Okay.
When we look at, as you said, that we take some random things on the parameter space, and then we move in a, then we take a step so that our probability is maximized. So
yes.
I just got two questions. How do we decide that the step length, and do we do this with the combination of all the 15 parameters, or we take it separately and then put it as one?
So generically, yes, we do it with all 15 parameters. That's why, I mean, basically you'll have 15 parameters which you'll have to run this MCMC or like some stochastic sampler on. And the steps, I mean, basically one very crude way to define the steps would be just to take a random number and take another point in the domain and then try to say, try to compare the probabilities between these two. And if the probability in going to the other point is increased, then you take that step. And if it's decreased, you also have a condition on how frequently you should take that step. So yeah, that's roughly the idea.
Okay, so if we are fixed about the taking the step length, so wouldn't this method would leave us to reaching a local maximum of probability? Okay,
that's a very good question. So the thing is that the Markov chain Monte Carlo samplers, especially, have this problem that there is like, let's say your underlying probability distribution has 2 peaks, right? And it could so happen that this, due to the MCMC, everything gets stuck in one of the peaks. And turns out that our, when you analyze data from LIGO-Virgo signals, the posterior distributions are actually extremely, have multiple peaks in their distribution. So that's why sometimes, I mean, actually most times we use these methods called nested sampling, which I've mentioned here on the slide, to actually calculate the posterior distribution in those cases. Nested sampling is actually very good at actually finding these multiple peaks in the posterior distribution, and it does that because I mean, just very briefly, nested sampling, the main function of nested sampling is to calculate the let's say the evidence that are described in the previous slides, and the fact that we get posterior samples is just a byproduct of that calculation. So yeah, so the answer to your question is that there are more advanced sampling methods like nested sampling, which are much better at finding these multi-peaks.
Okay, thanks, Aditya.
Great, thank you. Manuel? Manuel, we're having trouble hearing you. Manuel, we can't hear you.
Hello. Okay, perfect. Okay. First of all, thank you for the presentation. I like it. And I have a couple of questions. The first question is related with the noise, because we know that the real noise from the detectors are not Gaussian, are not stationary. So my question is, how the real noise affect this kind of methods? And my second question is related with, I don't know, maybe it is implicit in the question that you showed, but in any case, I have the question related to the assumption about the conditional probabilities in the Bayes theorem. Are you assuming conditional independence in conditional probabilities or conditional dependence between the parameters? This is my question.
Okay, so sorry, yeah, I think I'll try to answer your first question first. So I think what you were asking is how do we deal with the data which actually breaks our assumptions. So the thing is, this is one of the ways to estimate the PSD. So I mean, well, if we at least, and this method requires the data to be stationary and non-Gaussian over a large period of time. But there are other methods, especially the so-called Bayes wave method, which I didn't have time to go through, which actually does not need a very large data segment to really estimate the PSD. And it does so by actually fitting the noise by these so-called sine Gaussian wavelets. And that method turns out to be much, I mean, that method can estimate the PSD very well, even with very short time segments, so short that you don't allow your non-Gaussian and your say non-stationary features to play a role. But even if otherwise, for instance, the most famous example of there being a non-Gaussian artifact in our data is that of the GW17 node 17, which is the first binary neutron star merger. And in that, in the Livingston detector, we had a glitch right about when it was about to merge. So for that, we have to do, we have to provide, use data where the glitch is actually removed. say you put zeros in place of the glitch, or you fit the glitch by some sort of function and sort of remove it from the data, and so on. So that is how we deal with, that are, let's say, two broad ways to deal with non-Gaussian and non-stationary artifacts. I don't think I completely understood your second question though, but this is, I mean, so conditional, you asked of conditional dependence and conditional independence. So, I mean, I don't think I know much about what you're asking, but basically this is the probability of theta given the data, and this is the probability of data given the theta. So what we are essentially trying to solve here is an inverse problem, because we know what the data given a set of parameters looks like. So we are trying to find out what the actual values of theta are that explains the underlying signal.
Okay, thank you.
Okay, thank you very much. And we'll have one last question on this talk from Aman Berman.
Thank you, Mr. Vijaykumar, for your really insightful talk. I just had a small question. So is there a certain way of like determining or knowing what the sample size for the estimation is, or is it really just done by trialing different sample sizes to fit the observed data?
Sample sizes. By sample sizes, do you mean the number of samples here?
Yeah.
So that actually depends on a few things. So for instance, one very crude way to estimate the number of samples would be just, for instance, in this problem, is to wait till, let's say, the points from the prior actually sort of converge to this, let's say, like some small area in the parameter space, and then just take every move that the sampler makes after that and just collect all of them and plot samples. Turns out there are problems with this. There are some sort of correlations that exist, and we need to thin the samples that way. So in some sense, again, the point is that you always again want to choose the number of samples which will accurately allow you to define the underlying distribution well. So yeah, that's basically the answer to your question. So I mean, that could vary from problem to problem.
Okay, thank you.
Yeah.
Okay, perfect. Well, thank you so much for all of the questions. I appreciate all the questions that came in out loud, and also all the questions in the chat. Thank you to our mentors for, again, working furiously to keep up with the chat. So thank you for that. If we can all have a round of virtual applause for Aditya and show some appreciation for his talk. Thank you so much. That was excellent. We really appreciate it. And with that, we'll transition to our next speaker. So our next talk is going to be from Soni. Sid is at the MIT Kavli Institute, and he is going to tell us today about data quality.
Hello, everyone.
Hi, Sid.
Can you all hear me okay?
Yes, you are clear.
Awesome. Yeah, so today I'll talk about data quality in gravitational wave detectors. This is the overview. I'll start with LIGO strain data, then I'll move on to LIGO data quality. I'll talk about noise transients, the non-Gaussian noise transients that we have, auxiliary channels, category vetoes, hardware injections, and then I'll give a brief summary of O3 and our preparations for O4. I also have quite a few references, so I suggest you please check them out. They include lots of papers and other sources that will help you get a deeper understanding of most of the stuff that I'll talk about in these slides. So this is a very simplified picture of the detector. We have a laser, we have two 4-kilometer arms, we have a beam splitter and output photodetector. The essential idea is that a gravitational wave interacts with this system, changes the length of the arms, and then we read the strain in the gravitational wave channel, which is sampled at 16 kilohertz. It's more complicated than how I described it, because we have other things that also move these arms, and a lot of details go into this process of calibration. I've included a paper on calibration in the reference, and I suggest to read it if you want to find out the nitty-gritty details of how we do that. But we can ask this question, what does the strain data look like? So here on this slide, I have the raw time series, which this is how we start. We start with the raw time series, and I have 3 plots here. We have quiet data, we have noisy data, and we also have a gravitational wave. But if you look at this 6 seconds of data, so we have time on the x-axis and amplitude on the y-axis. If you look at all these 3 plots, you can't really tell which is which just by looking at them because they all look very similar. So we do quite a bit of data processing on top of this, this raw time series that we start with. So we start with the raw time series, but then we whiten the data and then we bandpass it. What do I mean by whitening? So as Becca also mentioned in her talk yesterday, the data that we have, the raw time series that we have, it contains a lot more power at lower frequencies than at higher frequencies. And that kind of overshadows or dwarfs the features at higher frequencies. So we whiten the data, and by that I mean we normalize the power in all these frequency bins so that the features at high frequencies are also better visible. Once we have whitened the data, we bandpass it. And what do I mean by bandpassing it? So we take a lower frequency cutoff and we take a higher frequency cutoff, and we say, I'm only interested in whatever is going on between these 2 thresholds. I'm not interested in anything, say, below 10 hertz or anything above 300 hertz. Just tell me what's going on between 10 hertz and 300 hertz. And when you do that, you find out some nice features. And there can be multiple reasons why you want to apply these thresholds, maybe because you already expect something within this frequency range. So after we do all this, as you can see from these plots, now some features are much better visible. If you look at the first plot, nothing much is going on there. The second plot seems like there's a big spike in the middle of the plot, so maybe there is a glitch. And the third plot, maybe you have seen this signature quite a few times by now, but that looks like a gravitational wave. So after that, after bandpassing it and whitening it and bandpassing it, we do something really dramatic. We QTransform this data. And QTransform essentially allows us to visualize this data in time frequency space. And as you can see, what we have now is much nicer. And we can clearly see the differences in the 3 plots. So we have the quiet data, as I said in the last slide, and then we have a rather loud glitch with lots of saturation in yellow. And finally, we have the gravitational wave. So this QTransform is really useful, and I'll talk about what QTransform is and how it does what it does. But essentially, it's really useful because it helps us with understanding the noise morphology. So how does the noise looks like in time frequency plane? It helps us with noise identification and classification. And again, a few slides down, I'll talk about the noise classification. And it also helps us with finding potential correlation with other parts of the instrument. So if you see this loud glitch in the primary gravitational wave channel, and then you see a similar looking glitch in other part of the detector, you may be like, okay, there is some connection between that part of the detector and the primary gravitational wave channel. So QTransform helps us with all of this. So just to summarize this section, we started with raw time series, and that didn't really help us much. But then we applied a bunch of data processing techniques, starting with whitening and passing, and finally obtaining a QTransform. And then we end up with something that's a lot more useful. So now let's talk about the LIGO data quality. So this is the sensitivity plot. You probably have seen this before. But this sensitivity plot essentially tells us how good a job we are doing or how sensitive our detector is. And the lower it is, the better it is, because then we can discover more gravitational waves. And so we do a lot of things to improve the sensitivity, both during the observing run, but mainly after the observing run. So once an observing run ends, we make a lot of changes that improve the overall sensitivity of the detector. And these changes include increasing the laser power, obtaining new test mass mirrors, because sometimes some issues with test mirrors can also reduce the sensitivity of the detector, employing light squeezing, which helps with the quantum noise, fixing sources of noise during an observing run is going on. We find out about a lot of sources of noise. And once the observing run ends, maybe we can fix those sources and have a better sensitivity. And we also have a ton of small improvements that go on helping us detect more black holes. So once again, coming back to this plot, we have seismic noise that dominates at low frequency, and seismic noise is because the Earth is constantly moving. It's always shaking at lower frequencies, and that diminishes our ability to get good data at those frequencies. And then we have short noise at higher frequency, and short noise is a type of quantum noise, which is due to the uncertainty in the number of photons that hit the photodetector, and that's why we have light squeezing, which helps with reducing the short noise. Okay, so short noise and seismic noise, these are Gaussian noise. These don't change. These are also stationary. They don't change from morning to evening or from 1 month to another. But we also have non-Gaussian and non-stationary noise, which we call transients. And I'll spend a lot of time talking about these transients in this talk. So what exactly are noise transients? One way to define them is that they are excess power over a very short duration, and we also call them glitches. So if you look at the plot on the right, this is a distribution of these transients over a day in February 2020. We have time on the x-axis and frequency on the y-axis, and the colors represents the signal to noise ratio. So how loud a noise transient is. How do we detect these transients? Well, we have a tool called Omicron. So Omicron takes in the strain data from the primary gravitational wave channel, but also from other auxiliary channels, and it finds these excess power in the strain data, and we call them Omicron triggers that you see on this plot. Every single dot on this plot is an Omicron trigger. Finally, what causes these transients? Well, there are a ton of things that can cause these transients: environmental disturbances, bad weather, thunderstorms, which are very common at near LIGO Livingston, ground motion, change in humidity in a particular subsystem of the detector, or anything going wrong with a detector component can cause these transients. So we have lots of reasons of why we may have these transients. So once again, our friend QTransform is back. I'm using QTransform now to show how these noise transients look in time frequency plane. Once again, we have time on the x-axis and frequency on the y-axis. And what I'm trying to show here is that we have different types of transients based on how they look in this time frequency plane. If you look at this Omicron plot, we can't tell much from this, like how these transients look or how they differ from each other, but we can use QTransform to do that. And why are these transients bad? Well, for more than a couple of reasons. They can mask a real gravitational wave signal. So for example, if you have a gravitational wave and at the same time you have one of these glitches, then you might not be able to see the gravitational wave properly, because usually these transients are louder than the gravitational waves that we have. They can also mimic a signal. So if you have a transient at LIGO Livingston and at the same time you have a transient at either Virgo or LIGO Hanford, then the analysis pipelines might get confused and think that we have a gravitational wave, when in fact we have noise. So they can mimic a signal, they can mask a signal, and they can reduce our confidence in the detection. These transients can also reduce our astrophysical range, which is a measure of how far we can see in the universe and how far we can detect the binary coalescence from. So for the duration that we have these transients, they can reduce our astrophysical range. The loud glitch that I showed you in one of the earlier slides is in fact infamously called range killer because of the awful impact it has on the range. These transients can also introduce problems for parameter estimation that Aditya just discussed in his slides. So the big question is, where do these transients originate? Well, these transients usually originate in auxiliary channels. So I only talked about the primary gravitational wave channel, but we also have tons of auxiliary channels. We have a channel that measures how much the test mass mirror is moving with respect to suspension cage. We have an auxiliary channel that looks at the beam alignment. We have auxiliary channels that tell us how much the ground is moving at different locations in the detector in the 3 XYZ direction. So we have tons of auxiliary channels, and sometimes something goes wrong in one of these channels, and if we are really unfortunate, it may permeate to the gravitational wave channel and create problems for us. So now this is a much more detailed plot of or figure of the detector. We have laser on the left here. Then we have the input mode cleaner, which is formed by IM1, IM2, and IM3. It's a triangular cavity. The input mode cleaner is used to clean the laser of the non-Gaussian modes. Then we have the power recycling cavity. You see PR3, PR2, and PRM. And the power recycling cavity increases the overall power that's incident on the beam splitter, which is right here. Then we have these 4-kilometer long Fabry-Perot cavity arms. And once the laser goes here, it spends quite a bit of time here, and because it moves back and forth multiple times. And this increases the overall interaction time of the gravitational wave with the laser. And so it has more time to leave its signature. And then we have a signal recycling cavity here, and we have an output mode cleaner, which is kind of similar to input mode cleaner, but it is a bow tie cavity, and it helps with cleaning the auxiliary lasers. And finally, we have the OMCT CPD, which is where we measure the strain. So this is a much more detailed figure, but it also tells you that we have so many subsystems, and each of these subsystems have so many auxiliary channels. So it's a really complicated network. It's a very complicated detector, and sometimes something can go wrong in any of these subsystem or any of these channels, and that can create problems for us. So what do we do about this transient noise? Well, the first step is to identify the noise. And when I say identify, I mean figure out its features. What is the duration? How frequently it happens? Is it more frequent on weekdays than on weekends? Does it have any correlation with trucks coming to the site, with thunderstorms? Is it more frequent in 1 month than the other? So the first step is figuring out all these properties of the transient noise. Once you have done that, the second step is to look for the potential correlations with the auxiliary channels and subsystems. So that means trying to find out if some other auxiliary channels or if some other subsystems have also noise at the same time we have noise in the primary gravitational wave channel. Once you have done that, the job is not yet done. It's still a correlation, maybe not a causation, but still a correlation. So the next step is to perform tests to simulate the noise. So now maybe you want to move some mirror or you want to shake some component of the detector to see if that would actually create noise in the gravitational wave channel. And if that happens, maybe you are in luck. Maybe then you talk to the people at the site and you say, hey, when we do something here, it actually creates noise in the primary gravitational wave channel. And if you can convince them of that coupling, maybe we can fix that source of noise to either reduce it or eliminate it. Sometimes all of this doesn't happen. In fact, most of the time, there is some issue with one of these steps, and we are not able to get rid of that noise. So then we develop vetoes. And I'll talk about what I mean by vetoes a few slides down. To do all of this, there are quite a few detector characterization tools or data quality tools that help us. We have Gravity Spy, we have QTransform that I mentioned a couple of times, we have HVeto, we have a scattering tool, we have Omicron that I also mentioned, and summary pages. So now in the next few slides, I'm going to look at some of these tools and discuss how they work and how they help us. So let's start with the QTransform. As I mentioned earlier, it helps us visualize the glitch morphology in the time frequency plane. The QTransform, it starts with taking the data and it projects the data onto a multi-resolution basis, which is parameterized by time, frequency, and Q, which is Q is a constant ratio of duration to bandwidth. So you can also think of, when you look at this figure on the right, you can also think of Q as the aspect ratio. So the QTransform creates these multiple spectrograms with constant Q, and then it optimizes over these planes and picks a plane which contains the loudest time frequency tile. And once it picks a plane, it means it has picked a Q. So you have what it returns at the end is a high resolution spectrogram with a specific Q value and with a specific event time and frequency. Next tool is Gravity Spy, and this is one of my favorite detector characterization tool, and I have been personally involved with it quite a bit. Gravity Spy is an image recognition algorithm which is based on convolutional neural network. I guess you guys have seen some of these algorithms which tell you whether it's a cat or a dog. Here we are using more than just two categories. We have We have gravity spy that helps us classify 23 transient noise in LIGO during the third observing run, and I have 6 of these categories here. This algorithm is trained on these time frequency spectrograms of noise transients. So we train the gravity spy first. We tell us that, hey, if it looks like this, it's a whistle. If it looks like this, it's a blip. And if it looks like this, it's a fast scattering. So we train this algorithm on a bunch of these noise transients examples. And then once we are satisfied with how it's performing, then we allow it, or then we use it to classify the transient noise that we have during the observing run. So it uses Omicron triggers as the input, and the output is the predicted glitch category. Now, Gravity Spy is really useful in the sense that Omicron tells us which day we have a lot of transients, but then Gravity Spy, what it does is that it tells us which day we had a specific type of noise transients. So for example, if there is a day with a lot of fast scattering, and then we go back and look at that day and we find that this day had a lot of trains passing by near LIGO Livingston, or it had a lot of seismic noise in 1 to 3 hertz band, and that's why probably we had a lot of fast scattering. So it helps us correlate the type of transients that we have with the conditions that may be present at the detector, and in that sense, it's really useful. We also have HVeto, which stands for hierarchical veto. And what HVeto does is that it finds coincidences, time coincidences between transients in gravitational wave channel and transients in auxiliary channel. So if you look at the figure on the bottom, this auxiliary channel has 6 transients. The H of T, the primary gravitational wave channel, has 5 transients, and there are a total of 3 coincidences. So HVeto finds statistical correlations between noise in gravitational wave channel and auxiliary channel, and then it assigns a significance to these correlations. What do I mean by significance? Significance is essentially quantifying how unlikely it is to have as many time coincidences compared to what you would expect from a Poisson distribution. So for example, you take 100 seconds of data and you find 10 coincidences, and you do this number of times, and most of the times on average you find 10 or 12 coincidences, and then one day you again take 100 seconds of data, and now all of a sudden you have 60 coincidences. So you're like, okay, now something special is going on. So that is what I mean by significance. HVeto progresses in multiple rounds. So the start of the round, it assembles all these coincidences. It assigns significance to these auxiliary channel, and the channel with the highest significance is declared a round winner. And at the end of this round, HVeto takes away all these transients which were found coincident with the round winner, and then it starts the second round, and it does it over and over again. So HVeto is really useful in helping us find the correlations between what's going on in the primary gravitational wave channel and some other auxiliary channels. So you can look at HVeto output, and then you can start your study from there, that maybe, okay, I want to look at this LSC, RAFL, ALF out DQ channel because this seems very correlated with the noise in gravitational wave channel. We also have summary pages, and they are incredibly useful. Well, summary pages contain the output of a lot of these tools that I mentioned, but it also contains a lot of information, real-time information about what is going on at the detector. So the first plot, for example, shows you the binary neutron star in spiral range at Livingston for this day. The second plot shows the vertical ground motion in 1 hertz to 3 hertz band, and we have instances where this ground motion goes really high. The third plot shows the output mode cleaner suspension point motion and the noise there. And as you can see, between 1 hertz and about 7 or 8 hertz, there's quite a bit of noise in that period from noon to 18 UTC. And finally, I have this plot of just the gravitational wave strain channel, the noise in that strain channel. Now, all these plots are from different days, so you won't find really any correlations here, but we use summary pages to study these correlations in different parts of the detector with the primary gravitational wave channel, but also to read the output of some of these tools that I mentioned. Slow scattering reduction. So a couple of slides ago, I showed you lots of transients, and one of them is slow scattering. Now, we had a lot of slow scattering during the third observing run at all the detectors like Livingston, Hanford, and even Virgo. And we were able to use these tools and more to figure out the noise coupling. We were able to find that there are two specific channels that were highly coupled with the noise, with the slow scattering noise in the primary gravitational wave channel. And we were able to go through all those steps that I mentioned earlier to establish this noise coupling and make changes so that after we were done fixing the source of noise, the amount of slow scatter was reduced drastically. So this is an example of how we can use these data quality tools to reduce the noise in the transient noise in the detector. What happens when we are not able to do that? Well, then we can develop these vetoes that I mentioned earlier. These data quality vetoes can be defined as flagged times. These are times when the quality of the data is not that good. We are not very satisfied with the data quality in these time segments. So we develop these data quality flags, and these flags are distributed in different categories that depend on not just the severity of the issue, but also on our understanding of the issue. So we have Cat1 vetoes, which is when there's a major issue going on with a key detector component. So either some key detector component is not working or some maintenance is going on and the data is not usable. So we don't really use that data. Then we have category 2 vetoes, which we apply when we have a noise coupling that we have a good understanding of. So we know that there's a specific channel which when has transients in it, it creates transients in h of t. So once we have a good understanding of the noise coupling for those transients, we can develop category 2 vetoes. The third category is when there is some statistical coupling, but that's not very well understood. So this is what H veto does. H veto tells you statistical noise coupling, but that might simply be correlation, and we might not be able to establish any causation. So in that case, we have these category 3 vetoes. These are all cumulative in the sense that if we have Cat1 veto, then we'll have all higher categories as well. We don't want to have a lot of time vetoed because then you're taking time away from observing gravitational waves. So at the heart of developing these veto is this principle of high efficiency and low dead time. So by high efficiency, I mean we should be able to develop vetoes in such a way that removes a rather large fraction of transients. And by low dead time, I mean that these flag times should be a small fraction of the total observing time. So we have to be really careful when we develop these vetoes. We also have hardware injection, and hardware injection is when we inject a signal that actually moves one of the test masses. We do this to establish the safety of vetoes and to create a list of safe and unsafe auxiliary channel. So we inject these sine Gaussians at different frequencies and amplitude because we want to check over a broad range of amplitude and in different frequency regions, and that helps us establish the safety. So what do I mean by safe auxiliary channel? A safe auxiliary channel is one which does not respond to hardware injections in primary gravitational wave channel. And such a channel can be used to develop vetoes for primary gravitational wave channel transients. We can't use unsafe channels because say you have a gravitational, we don't want to use unsafe channel because unsafe channels are sensitive to primary gravitational wave channel, and mistakenly you may veto a gravitational wave. So for example, if you have a gravitational wave in the primary gravitational wave channel and then you have an unsafe auxiliary channel that is sensitive to it, so it may have some transient, and if you veto that transient, if you take out that time, then you're essentially taking out the gravitational wave. So it's very important to have this list of safe and unsafe channels because only safe channels can be used to develop the vetoes, and for that we perform these hardware injections. Finally, I'll give a brief summary of O3 and our preparations for O4. So O3 was split into O3A and O3B. O3A was from April 1 to September 30, and O3B was from November 1 to March 27, 2020. We had a total of 74 gravitational waves detected in that time period, 39 in O3A and 35 in O3B. And I suggest to go over the our catalog paper that includes a lot of details about all of these events that we have discovered. They included signals from binary black holes, binary neutron stars, and even neutron star black holes. The plot on the bottom left shows the range during O3b of LIGO Livingston, LIGO Hanford, and Virgo. And the plots on the right show us the observing segments. So if you look at the network duty factor, the pie chart on the bottom, that tells us that about 44.5% of the time, we had all the 3 interferometers observing at the same time. About 37% of the time, we had at least 2 interferometers. So either LIGO Livingston and LIGO Hanford, or LIGO Livingston and Virgo, or Virgo and LIGO Hanford. So we had at least 2 interferometers observing. And 15% of the time, we only had 1 interferometer, and at about 3%, we did not have a single interferometer observing. So as you can see, at least 85 or 82% of the time, we had at least 2 interferometer, which is really good. Preparations for O4, the plot on the figure on the top right shows you our expectations from O4 and O5. We are expecting a range of about 160 to 190 megaparsec for LIGO, and this is binary neutron star range. Similarly, for Virgo, we are expecting a range between 80 and 115, and Kagra would be joining us with an estimated range between 1 and 3 megaparsec. O4 currently is scheduled for to begin in December 2022, and there are quite a few changes that we'll have in O4. We'll have new mirrors, we'll have higher laser power, and possibly mitigation of low frequency noise that will help us with the sensitivity. And all of these changes will help us with a better sensitivity and a lot more gravitational waves. So thank you very much for attending this talk, and I'll be taking your questions. As I said, we have lots and lots of references here that I suggest to check out that will help with these slides. Thank you.
Perfect. Sid, thank you so much. That was a great talk. So we will pause now to see if there are questions. If you do have a question, please use that hand up feature in the chat.
Luis.
Okay. Luis, do you have a question?
Okay, Professor Sid, if you make a Q graphic of the event 190814, what Q factor did you choose? A low Q or a high Q?
Well, it is possible to choose the Q factor yourself, but what this QTransform does is that it goes over a range of Q values. So you can set the range of Q values and then automatically selects that plane which contains the highest signal energy. So you can change that range and then it will optimize over that range and find a plane with the highest signal energy, and that would be your Q.
Yeah, because I am doing the Q graph, and the Q graph is like a neutron star, but the Q that I have to choose is a low Q. And if it is a neutron star, it has to be a high Q. There is some contradiction. Can you explain this?
If you are using the GWPy time series.QTransform method that I have mentioned here, you should be able to set a Q range, and then it would be restricted in finding a Q within that range.
Okay, thank you, Soni.
Okay, perfect. Let's see, any other questions for Sid? Okay, perfect. And I did see a lot of questions go by in the chat, so thank you all for that. Thank you again to our mentors for all the answers. Maybe a special thanks to Professor Alan Weinstein, who's been furiously answering questions in the chat over all 3 days of the workshop. So we're very grateful for his insight on all these many questions. Let's thank Sid one more time if we can. Thank you, Sid.
Thank you, everyone.
Very good. All right, and so with that, we'll transition to our last topic for this session, which is a check-in on the tutorials for today. So I can share my screen. And of course, these tutorials are designed to go through at your own pace. I'm sure every person in every study hub is moving at a different rate, and that's fine. So wherever you are, I hope you'll continue working through the tutorials today and over the next few days. Of course, today's talks focused on CBC parameter estimation and on data quality. Some of those data quality topics you'll find here under working with GWPy. And then parameter estimation topics you'll find here under CBC parameter estimation, and there are tutorials to go along with that. You can actually try out Bilby, which would be great. And then the thing I wanted to touch on today is the data challenge. So this set of lectures will be our last lecture session for the workshop. We're inviting everyone to participate this year in a data challenge. When you're into Thinkific, you'll find a link here that says try the data challenge. Instructions for the data challenge are here, and that's this link, which will take you to a README file in our GitHub repo, and that's here. And all the instructions for the data challenge are here. So here are the data files that you'll use for the challenge. There are instructions up here. These different numbered challenges, these are the questions. So challenge 1, and here are the questions, challenge 2, and here are the questions. So the challenge is divided into these 4 levels, if you like. And then also do note down here at the bottom are some useful notes. So here are some hints to help get you started. For example, there's a wget command. If you are working in one of these online platforms like Colab or Binder, then you will want to use these wget commands to download the challenge data files into your work environment. So there's some helpful code snippets here that should help get you started. And of course, you can find lots of hints in the various tutorials. So the tutorials over the whole workshop are intended to teach you the commands and skills and data processing techniques that you'll use for the challenge. And then after you've had a chance to get to work through it, in the Thinkific, there's a heading here to submit your data challenge solution. I believe Thinkific will only let you submit your solution once. So I do encourage you to try and work through the challenge before submitting your solution. And what you'll do is you'll write your answers into these text boxes, you'll click confirm, and you'll click through. And then at the end of it, you can submit your solution. We are setting a target date of 1 week from today to have in the solutions. So that's June 1st, I believe. And so after that date, our mentors will go through and make an effort to score whatever solutions we've received by that date. I see there's a hand up, Isaac.
Hi, Jonah. Yes, we have some students in our study hub that try to join this online course, but they were put in a waiting list. So they are asking if it didn't receive a later email. So they are asking if they can, go with this content and post their challenge answers.
Yes, of course, they're very welcome to participate. So this Thinkific course, one of the reasons we put the course material into Thinkific is because there's no registration cap on that. Our intent is to make these materials as easy to access as possible. So yes, they are certainly welcome to participate in the data challenge.
Oh, okay. So they can, they should be able to see this online course in the WOSC site.
Yes. So if you start from the workshop webpage here, and you scroll down, so this is a webpage, it's open to everyone. And if you scroll down to tutorials and online course, here's the button for the online course, and that will take them to the Thinkific, and then they can register there and work through the materials. Perfect.
Great, thank you.
Yep.
Professor Kanner,
Yes, Luis.
I would like to know if it is the last day of the course of the sessions.
Yes, this will be the last day for the workshop. Of course, all of
Do you have any? Do you plan any posterior events like the last year with the our office, or you are still thinking about that?
Yeah, so we're trying to encourage, for follow-up discussion, we're trying to encourage the use of our new discussion forum. So we've got this ask.igwin.org, which is a discussion forum that we're now making available. And so we're trying to encourage the use of that for posting questions. We think that's really valuable because if people post questions, then one, it becomes a community project to answer those questions. And two, those questions are now, and their answers are now available online and can be searched, for example, can be discovered by search engines. So if I go into a search engine and type, I have a problem, why do I get this error message with Bilby? Then maybe in the future, that search engine will be able to find that answer on the discussion forum. So we are trying to encourage folks to use that.
So I want that you know that a lot of people will miss you. 1 year is a long time. Sorry.
Okay.
A good job as always.
Yeah, that's very kind, Luis. And of course, we're pretty easy to find, so folks are always welcome to reach out and contact the GWAS development team if you have need additional support. I do see there's a question in the chat. I'm studying grade 11. Yeah, so the data challenge, so all the materials for the workshop, including the online course, will remain available online indefinitely. So the 1 week deadline, that is in order to have the opportunity to have your data challenge solution scored. But if for some reason you miss that deadline and want to work through the materials at a later date, that of course is okay too. I just can't promise we'll get back to you. Yeah, so there's a question for the online challenge. Do we submit just our answers or do we also include our work? If you'd like to share your solution and your work, what I'd recommend is put your solution into a GitHub repo and send us a link, and that's fine. So if you want to, or some other online sharing platform, if you want to share your solutions and make them available for folks, of course, you're welcome to do that. Okay, other questions?
I have one, if possible. I am, let's say, from Italy. For what concerns the question of the data challenge, at some point, once the data challenge is over, will you post also the answer for that, or this will remain a challenge also for future applicants on the online course?
Yeah, so most likely both. It is fine for folks who've completed the challenge to what I'd suggest is, if you'd like access to solutions, then reach out to us and we can share solutions after that June 1st deadline. So I see there's a question, do we have to get every question right to get the certificate? The answer is no. It is a certificate of completion. So that the certificate of completion will be awarded through the Thinkific platform upon completion of the course. I should say the data challenge is intended to be somewhat challenging. So, do the best you can with it. It is an open-ended challenge. So in principle, in principle, you can push it as far as you'd like. And so I'd encourage you to spend some time with it and see how far you can get. Yeah, and Alan makes a good comment. We certainly do encourage you to work in teams. So if you'd like, particularly, for example, if you're in a study hub and you'd like to make groups of, say, 2 or 3 people, that's certainly encouraged.
So, Professor Kanner, I would like to express my gratitude to all of you. The great effort every year. I know so hard is to do it. I know so hard is meeting all the professors, the organization. It's a great effort. You got my heart. Thank you.
Thank you for saying so, Luis. That's very kind. Yeah, there is a good deal of effort that goes into planning these workshops. So thank you for saying so. In fact, maybe that's a good note to end on. We do want to express gratitude and appreciation for all of our mentors who prepared the materials, prepared the tutorials, prepared and presented lectures, are answering questions in the chat, are continuing to answer questions on ask.igwin.org. We'll continue to answer questions on ask.igwin.org in the coming months. So thank you so much to the folks who put these materials together and are supporting this workshop. Thank you to all the participants for taking your time and for your interest in gravitational wave research. We really appreciate it. And I think with that, we'll close the session. Thank you all so much and good luck with the data challenge.